So speaking about Brownian motion, one has to start with Einstein, who I think developed the first foundation of mathematical theory of Brownian motion. He did it in the same year as he did three other famous works. So this work are this famous formula EMC square, special relativity for the electric effect, for which he got Nobel Prize, and also a paper about Brownian motion. If you consider mathematics, then Brownian motion is by far the most complicated of these four, because say for special relativity, Minkowski developed mathematical foundation just 2 years later. For Brownian motion, people developed foundation much later, like Wiener in late 20s and then in 30s, but still a lot of questions actually are not settled. So I think mathematics, there are many open questions. In particular, some of questions I'll address today. So what Brownian motion in mathematics is usually called Wiener process, and it has Gaussian transition probabilities. This is, of course, what Einstein understood. And in particular, there is this fundamental relation when distance scales like square root of time. And maybe this is one of important discoveries of Einstein. A lot of probabilists studied Brownian motion, so it started with Dubh, Feldher, Levit, Kolmogorov in the 30s, but then after World War II, really there is a long list of people who studied it. But actually this knowledge, I think, did not percolate it to physics yet. There is a lot of knowledge about Brownian motion developed by mathematicians, which is not used in physics. So speaking about this Gaussian transition density, later De Giorgi, Nash, and Moser proved that similar kind of transition density exists for elliptic and parabolic PDEs, for non-continuous coefficients, and so on. And then Li and Yao did obtain famous result that on any geodesically complete Riemannian manifold with non-negative curvature, you also have estimates for transition probability of similar kind. What is important here is that there is a volume term, so it could be in any dimension, and you could have a manifold which grows whatever speed you like, provided this condition. This is very restricted condition. But off-diagonal terms behave in the same way as case of Gaussian transition probability. So I think a lot of people believed that this is a universal behavior. But at the same time, in mid-80s, some people who did numerical work understood that there are so-called, it could be sub-Gaussian behavior, where you have an exponential of some power of distance, and this power may not be a square. In principle, there are two different powers here, one power for time and one power for space. But for some reasons, I will not explain it here, there is just one parameter. Time and space have to be related, so there is room just for one number. But this number doesn't have to be true. It could be a different number. And more generalized space-time dimension looks like this. The distance scales like a time to some power, which is convenient to write as 1 divided by a number. And this number got a name, work dimension, which is really very unfortunate because this number is not dimension at all. You see, in any Euclidean space, this number is true. So in any dimension, number is true. And if it's not true, it just means that space is not Euclidean. It doesn't mean that it's for larger spaces, this number is larger. So the first situation where this phenomenon was observed was when mathematical physicists studied transport properties for disordered media, such as critical percolation. They observed that diffusion moves, or random walks moves, but it moves not as fast as classical Brownian motion. Distance, if you measure expected distance, it grows as a power of time, but power is strictly larger than 2, which means that displacement is much smaller than for Brownian motion. And then mathematically, the first situation when this was proved was on Sierpinski gasket. It was in mid-80s, and it was proved that one really can have a diffusion process, which is one well-defined in terms of as a Markov probabilistic process, which has transition density of this form. So there is a power which determines how probability decays with distance, and this power is larger than 2. It's called walk dimension. And then there is a different power here, which is called spectral dimension if it is multiplied by 2. So actually, I know some people very much object to this number of 2, because this number of 2 here is inherited from Euclidean space, that in Euclidean space you have dimension divided by 2 here. But in principle, if you study more general spaces, it should not be here. So, and again, walk dimension is certainly not a dimension, and spectral dimension is actually also not a dimension. So these two numbers are some numbers which measure how space is connected. Of course, this first dimension, which is Hausdorff dimension, is well defined. This is classical quantity. But these are two parameters of space, which are certainly very important, but they're not dimensions. So it was first discovered for Sierpinski gasket, and then a lot of probabilists started to study this process, because historically it was the first diffusion process which does not go to Einstein as a background. So it was defined in completely different way. So these are some pictures. This is Sierpinski gasket and another typical fractal in Strom snowflake. And very soon after studying Sierpinski gasket, people moved to another object which is called Sierpinski carpet. And this fractal is universal. It appears in many subjects of mathematics, in particular in hyperbolic groups and things like this. There is a lot of universal properties of this fractal, and people naturally wanted to define diffusions on Sierpinski gasket. Since this is an introduction, I wanted to show also a picture of Sierpinski. And this is the paper where he defined Sierpinski triangle. And in particular, from the pictures in this paper, you can see that he actually thought about walks inside of these fractals. He did not think about random walks, but this is more like safe-Walden walk. So in a sense, what we are doing, we are combining vision of Sierpinski and Einstein to put diffusion on this universal object, Sierpinski carpet. And as continuation of introduction, recently there is very surprising source for fractal models. This came from algebra, from group theory. In group theory, there are self-similar groups which are related to finite automata. And relatively recently, they stumbled for a group which is related to Hanoi Towers game. And for these groups, there is a limit space, which is, people understood that it could be a fractal, but for this particular group, it actually happens to be Sierpinski gasket. I think it was discovered, the paper was published in 2006, so it's really only recently. And then if you continue making connections, these finite automata are related to how words of numbers are processes. So you could go to really to algebraic equations and then to computer science, and finite automata originated by Noam Chomsky. So next I will show more pictures of fractals just to illustrate what kind of fractals we consider and what kind of fractals we would like to consider. For me, the first example of fractal is a unit interval. A lot of people will object once we wrote a paper and this was the first example, and referee wrote that unit interval is not a fractal. But for us, it satisfies all the properties. So it is self-similar, it has one-dimensional, and so on. So every result which I say is true for one-dimensional interval. Then next complicated Next classical example is Sierpinski gasket. Generalization of this is nested fractals. So this is typical nested fractal. Then it was generalized to so-called post-critically finite self-similar sets, which are abstract objects but have similar properties. And slightly larger class are finitely ramified sets. So this is important distinction. In examples like this and this, there is finite ramification property that it's possible to remove finite number of points, so fractals get disconnected. For example, for Sierpinski gasket, it's enough to remove these 2 points, and the entire fractals gets disconnected. Say for unit interval, it's enough to remove just 1 point, and it is disconnected. Analysis on such fractals is much simpler than on fractals which are not finitely ramified. So this is another example of fractal which is finitely ramified. And incidentally, this fractal has dimension 2, intrinsic dimension. So there is this naive point of view that fractals are object of fractional dimension, and this is not true. So here dimension is integer, but it is still a fractal. And then this is a set of fractals which you discovered relatively recently, and this illustration is good because it shows that really fractals look like quantum graphs. This is why my talk may be appropriate here, that to build a fractal, you can consider approximating quantum graphs and make edges shorter and shorter. You also make them thinner and thinner, and as a limit, you get a fractal. This particular fractal, it is very complicated. It is not embeddable in Euclidean space, but good thing is that you can compute spectrum completely. You can compute all eigenfunctions, eigenvalues, and compute, for example, spectral zeta function. And yet you can build it in any dimension, not integer. So this space, it could look very complicated, but actually it's the best analog of Euclidean space in fractional dimensions. So this is Sierpinski carpet. And for the study which we did, initial motivation or some physics papers. So a famous paper is by Ramal and Toulouse, and also there are other physicists who studied, like Domani, Alexander, Ben Simon, Kadanov, and Geffen, Ahern, and Monderbrot. And from the title of the first paper, you can see that they considered fractal structures as simple models for percolation clusters. So the motivation was to study critical percolation, and natural guess would be that it's too complicated, so let's build a simpler model which has similar features, and then fractals were considered maybe given a similar model. What these people understood that such kind of fractals like Sierpinski gasket is relatively easy to analyze. And also they understood that it does not behave like percolation cluster at all. So this initial work did not continue very far, but I think mathematicians continued to study it, and what we realized much later, like 25 years later, that actually fractals are very much like percolation clusters, but only you have to consider different fractals, more complicated. So after these initial physics papers, Sheldon Goldstein showed that if you take random walk on Sierpinski lattice, as written here, and you start to rescale time in some non-trivial way, then you can get a diffusion process. And maybe a better, more precise result was obtained by Kusok at about the same time. Now, it's important here that you scale time as a power which is not integer, is a ratio of 2 logarithms. And this is the source of these fractional walk dimensions and spectral dimensions. That you have a random walk on a graph, which could be a finite graph, and of course it's very easy object to define. But then you'd like to have a limit which is non-trivial, which moves but does not move infinitely fast. And to do this, you need to rescale time. And then this number somehow is unique. For Sierpinski gasket, it could be computed easily. So it's unique and it is not integer. Then after that, in physics, it was some interest, but maybe even more interest it was in probability community, because this diffusion process was something unusual, and a lot of people started to study it. So Barlow and Perkins, they obtained this sub-Gaussian transition density estimates for Sierpinski gasket, and then the next year Barlow and Bass proved existence of Brownian motion on Sierpinski carpet, which is much more universal object. But what was unfortunate is that they could not prove uniqueness. Like for Sierpinski gasket, it's not stated here exactly that diffusion exists, but you can easily prove that it's also unique up to natural symmetries. For Sierpinski carpet, situation was different, that they proved existence, but we could not prove uniqueness. And a lot of people continued with research, but in question of uniqueness, it was no progress really in the previous 20 years. So this I probably will skip. So the main part of my talk is to review of this proof of uniqueness. The paper is published this year, and the proof is very long. We tried to make it short, but we could not. So this is the outline of the proof. We start with some general properties of Dirichlet forms, which is generalization of usual notion of energy. And this object is not random. But then in the middle we had to go to random processes, because it was an important step which at least now can be done only probabilistically. This is so-called coupling. And then after considering Markov processes, we had to go back to analysis, and this probabilistic technique, coupling, is needed to prove elliptic Harnack inequality. And after elliptic Harnack inequality is proved, there are a lot of estimates which are new but by now well known, which could be used, and this implies uniqueness in the end. So I will explain only briefly how the proof works. So this is a statement of main theorem. It basically says that there is a unique diffusion on Sierpinski carpet. Then one of the main ideas is this. We have this space which is defined geometrically, and our aim is to prove that all possible Dirichlet forms or energy forms are bounded. There are universal bounds which depends only on geometry. And then there is one trick which nobody used before, but it's not very difficult, is that if you have local Dirichlet forms, which corresponds to random processes with continuous trajectories, you can subtract one of the other, and you still have an energy form. So, and then it leads to contradiction. If you have two possible energy forms, you could certainly have a convex linear combination, but you also can have a linear combination which is not convex. And then here you get a contradiction, that you can have a Dirichlet form which doesn't satisfy this universal bound, which is geometric. And this contradiction is to the fact that I assume that there are two different Dirichlet forms. So by contradiction, there is just one, and it proves uniqueness. So the main this part is relatively simple. The most difficult part is to prove these universal bounds, which are based on geometry. Then I will skip a lot of steps. I try to skip as much as I could. Bounds in Hilbert projective metric. I will. It's typed, but in the end of my talk. So here there is an illustration of results which we use, and these are abbreviated because otherwise it will be too long. So there is a notion of volume doubling, elliptic harmonic inequality, and resistance estimates. And it is proved in very high generality that it's equivalent to heat kernel estimates. And this is the goal which we would like to use, because these things we could estimate geometrically, and then it leads to probabilistic estimates. So these are some general properties of Dirichlet forms. Basically, this result says that we can subtract Dirichlet forms if they're regular and local and still get a Dirichlet form. And this is actually important result because this is not true on graphs, but this would be true on quantum graph. So there is this point of view that if you do combinatorial graphs, it's always simpler than quantum graph, than continuous object, such as quantum graph. But this is one result which is true in continuous case, but not true in discrete case. And the reason is that to have a Dirichlet form in discrete case, you need a matrix which is positive definite, and also all of diagonal matrix entries are positive. And if you subtract these two matrices, you can have a result which is still positive definite, but entries are negative. But in local, in continuous situations, apparently does not happen. So this I skip. This is definition of fractals which you consider, and these are some related pictures. Then one of the technical things which we had to use is how to relate geometry and analysis. And this definition is very complicated, but I can illustrate it very easily. Namely, consider this to be a carpet, and then what you can do, you can fold it into much smaller carpet, and this smaller carpet is similar to original one. Now suppose you have a random walk here, somebody is going random walk around Cambridge, and then you fold it, and you look how this random walk looks here, and then it still will be a random walk, and it will be reflected at the boundary. So this is very nice probabilistic description, and the important thing here is that to define it, I don't need to worry what kind of transitional probabilities I use. It still will be reflected random walk. What is important is this random walk is continuous. If you allow to jumps, then this construction will not work anymore, because if it's technical complication, but important. So another important technical result is this. Using this, what we call folding map, which basically behaves like folding a map, we can define induced object on functions. And then important result is this item B here, that this transformation of functions computes with energy. And basically from this commutativity relation, in a lot of steps we can obtain this uniform estimate. Yeah, and of course, as usual, if something computes in Dirichlet forms, then say semigroups also compute. And then from computation relation for semigroups, one can obtain some estimates. But the thing is that this, of course, pure analysis, but after that we had to go to geometry and to study how processes behave. Now, at this point, the main difficulty was to prove that our diffusion moves at all, because it is a fractal, and what you could imagine that diffusion moves a little bit in some regions of it, but it does not go any large distance. So the technique for this was developed by Barlow and Bass in '89. They introduce a different kind of moves. Say if you are on half phase here and a half phase here, you need some non-zero probability to go to one half phase to another half phase. And this is illustration of what we'd like to avoid, because you see they pretend to move, but they don't move. And this is what would like to prove, that diffusion really moves a non-zero distance. And then, as I mentioned before, Analytically, this probabilistic technique is used to prove Harnack inequality. And this Harnack inequality is completely classical formulation. But if you have two non-negative harmonic functions, then in a ball of, you can estimate maximum in a ball of smaller radius by minimum. Actually, I think, yeah, there is a typo here. One of these two r's should not be divided by 2. So you estimate supremum of a larger ball by infimum in a smaller ball. Yeah, sorry. But perhaps the type is because I did not pay a lot of attention. It's really classical elliptic Harnack inequality. But it's surprisingly very difficult to prove. So it's much more than half of this paper is devoted to prove this inequality. And what is important here that we really don't know what diffusion exists on this space. We used only geometric information to prove that this inequality is true. And after that, there are known techniques to, we can prove that harmonic functions are Hölder continuous. And after that, we can prove a lot of irreducibility properties. And after that, we prove resistance estimates and then heat kernel estimates. And we get to these results that if you have volume doubling, elliptic Harnack inequality, and resistance estimates, you get heat kernel estimates. And then from heat kernel, one defines different function spaces. And this is analog of Sobolev inequality. It's of course stated in such a way that it's not recognizable, but in principle, what it says that this energy in terms of analog, it's like integral of square of the gradient. So, and fractal gradients does not exist, but this is how you think it. And Sobolev inequality, at least in some forms, compares energy to some other integrals. And here you have to compare energy to some Besov norms. Yeah, and after all this work, we can come to final section to prove uniqueness. Here there is a formula for Hilbert projective distance. If you have two quadratic forms, then you define a supremum of these two forms, just a supremum of ratios, and you define distance between two quadratic forms as logarithm of supremum b of the a divided by supremum a of the b. So it's really was introduced by Hilbert. And then the theorem which we proved is that any Dirichlet form on such a space as Sierpinski carpet has to be in some fixed ball, like what I illustrated on this picture. There is some universal estimates. And then if you think about this first theorem, that if you have two different Dirichlet forms, you really can form a linear combination of them and still be in the same class. And this is contradiction to non-uniqueness. So this implies uniqueness. I wish we had a simpler argument, but we could not. Still, it took 20 years to develop it. What is interesting, I talk always about diffusions, but actually it implies uniqueness results for graphs, because you can build an infinite graph which has the same structure as the Sierpinski gasket, and you can define random walks which are self-similar. And you can pose the same question if this self-similar random walk is unique or not. And as a corollary, you can get that it is unique. But at the moment, there is no direct proof on a graph. You could imagine that graph should be simpler, but it seems it is not. So this proof, as I mentioned, it certainly uses that space is continuous. And in a sense, it shows why quantum graphs may be better than combinatorial graphs, because quantum graphs are continuous. So I really did not want to go into many details because there are too many of them. What instead I will do as an appendix to my talk, I will show something about spectral results. What I should say that spectral results are possible only on much simpler fractals. So this goes back to Sierpinski gasket. we would like to have spectral Sierpinski carpet, but so far it was completely impossible to obtain. And one paper I'd like to mention, it was published last year, and authors are Eric Ackermans and Gerald Dunn. Ackermans was already mentioned today because he studied spectral determinants on quantum graphs. And when we met, the natural question was, we could study spectral determinants on fractals, why not? And it's possible to compute spectral determinants on fractals, but what we discovered is that there are some even more basic things which are not quite well known in physics community. So in this paper, what we published is that if we consider very simple graphs, very simple fractals, which are even simpler than Sierpinski gaskets, we call them diamond fractals, you can compute explicitly heat kernel, and heat kernel oscillates at small time. So a naive view was so far that if you consider diffusion process at large time, it could have very complicated behavior. But at small time, everything should be averaged out, and it should sort of go smoothly in a small ball. But what you can compute quite easily, that it does not go smoothly. You take a time which goes to 0, and your heat kernel oscillates. And so it starts oscillates infinitely fast. What happened before is that before people computed it numerically, numerical computation on fractals are quite complicated. So they would compute just one bump or maybe two bumps, and they would say that it's numerical error or something like this. But in this simple model, you can make a theoretical computation explicitly, and you can see that there are infinitely many oscillations, and it's not a numerical error. So this is one of these important features of fractal models. And in the last 5 minutes, maybe, I'd like to present briefly a recent preprint of this year. We wanted to do it long time ago, but we finished only in the summer. So if you have fractals, an X-natural object was introduced by Strickers, and he called them fractofolds. These are objects which have some global structure, but locally they are like fractals. This in particular picture, it is based on a binary tree. So you imagine a binary tree, and then for every vertex you put a Sierpinski gasket. And then you get an object which has a lot of nice symmetries, and in principle you could expect that it's possible to compute spectrum. And we knew that it's possible to compute spectrum, but now we finally did. And I will briefly review what is done. Of course, usually you start by computing spectrum, but because situation is so nice, we made a larger goal. We wanted to compute Poincaré formula, and even more basically wanted to write a complete Fourier analysis. And Fourier analysis can be written in terms of, again, function expansion for Laplacian. But of course, Laplacian does not have to have discrete spectrum. So it could be a continuous spectrum and discrete spectrum. So we would like to write a function as an integral of the spectral measure using spectral decomposition. In Euclidean case, it would be just exponential functions here. And then on Lie groups, there is well-known representation theory. And we wanted to see how it goes on fractals. So this is Sierpinski gasket again, and this is definition of energy, which I did not give before, but it's quite simple. You approximate Sierpinski gasket by graphs. On a graph, you define usual energy, and then you multiply by some strange factor 5/3 to the n, and you obtain a limiting energy. Then it is here done for combinatorial graphs, but you can do exactly the same for quantum graphs. You just use slightly different normalization, but the difference in this case is not important. And if you have energy form, you also can define Laplacian basically by integration by parts. There is some number here which is replaced by historical reasons. It's not important. And Laplacian will be self-adjoint if you impose Dirichlet or Neumann boundary conditions. And then our aim is like this, to build a fractal fold, for example, like this. You start with a combinatorial graph, like a tree, and then you put Sierpinski gasket in every vertex. So I assume that combinatorial graph is regular of degree 3, and I assume the spectrum is known. So what I'd like to know is how to relate spectrum on a graph to spectrum of this fractal fold. And then one can write a abstract theorem. I will not explain it, but basically you can write everything explicitly. There are analog of exponential functions which allow us to write something like Fourier transform. So one of the examples is so-called infinite Sierpinski gasket. It was first considered by Barlow and Perkins. So it's like Sierpinski gasket on a small scale, but also Sierpinski gasket on a large scale. And in this case, there are two paths which are sort of glued together. And then spectrum is quite complicated. So there is some kind of transcendental function, and you compute spectrum on a graph, and eigenvalues are algebraic numbers. But then this transcendental function transforms then into eigenvalues which are not algebraic, but all eigenvalues are computable explicitly. What happens is that there is a dense set of eigenvalues of infinite multiplicity, but in addition there is a singularly continuous component which has spectral multiplicity 1. And this second part is very complicated. It was proved by Quint, published only last year. So this pure point part was proved by me more than 10 years ago, but singularly continuous part is much more complicated to obtain. This is another slide which shows which you would like to have. In particular, we have a conjecture that if you have a relatively nice Laplacian, there is a generalized eigenfunction expansion. And what we'd like to have is on eigenspaces some kind of generalized inner product, so that you know, if you have a finite matrix, then eigenfunctions for different eigenvalues are orthogonal. And we'd like to have a continuous analog of it for generalized eigenfunctions. And so far, we could not find in the literature result which is written in this form. There are results about generalized eigenfunctions, but they are of different nature. What is different is that for generalized eigenfunctions, they are usually defined in terms of distributions, and you have two different spaces, like test functions and so on. But what we'd like to have a Hilbert space, so this just should be an inner product. And on this example, we actually were able to obtain it, and this inner product is surprisingly simple. It's just average of a ball of radius n. But this is actually very surprising because it is a tree, so ball grows exponentially. So you would imagine that you define by some function, maybe some power of volume, but it is not. So this n is like logarithm of volume. And surprisingly, on a tree, of course, spectrum is absolutely continuous, so these generalized eigenfunctions decay, but they are not L2 eigenfunctions. And what is surprising is that you can introduce inner product on eigenspaces, and it looks so simple. And if anybody saw something like this, then please let me know, because binary tree is a very well-known object, and harmonic analysis on binary tree is well known. But this particular result we did not find out. So this result is just for combinatorial trees, not for fractals. Oh, we do, we prove, yeah. It's part of the proof that the scalar product is independent of base point. So this is illustration of some special eigenfunctions. So on a tree, if you apply this abstract theorem, you get that there is absolutely, for fractal there is absolutely continuous spectrum, and there are some special eigenfunctions like this. And another set of examples also we considered periodic fractal folds. We used results of Couchment very heavily, and then examples could be like this or like this. So this is really a periodic lattice which uses Sierpinski gasket as tiles, or like this, for example. For this, I have a picture of spectrum, and spectrum, it has absolutely continuous components, which is made of bands, and then eigenvalues, some of them are isolated, some are in the edges. So the result is sort of predictable, and we could say a very long time ago that spectrum should look like this. But what is important is that we can make exact computation, that it's not a qualitative picture, it is quantitative. Okay, so this is the last slide. Thank you for your attention.